Hello everyone, my name is Ravana Jyoti. In this session, we are going to discuss about multi-threading models. Multi-threading allows the execution of multiple parts of a program at the same time. These parts are known as threads and are lightweight processes available within the process. Multi-threading allows the task to be divided into multiple threads. Therefore, multi-threading leads to maximum utilization of the CPU by multitasking. In an operating system, threads are divided into user-level thread and kernel-level thread. User-level thread. The user-level threads are implemented by users, and the kernel is not aware of the existence of these threads. It handles them as if they were single-threaded processes. User-level threads are small and much faster than the kernel-level threads. They are represented by a program counter, stack, registers, and a small process control block. Also, there is no kernel involvement in synchronization for user-level threads. Advantages of user-level threads. Some of the advantages of user-level threads are as follows. User-level threads are easier and faster to create than kernel-level threads. They can also be more easily managed. User-level threads can run on any operating system. There are no kernel mode privileges required for thread switching in a user-level thread. The disadvantages of user-level threads are multi-threaded applications in user-level threads cannot use multiprocessing to their advantage. The entire process is blocked if one user-level thread performs blocking operation. Kernel-level thread. Kernel-level threads are handled by the operating system directly, and the thread management is done by the kernel. The context information for the process as well as the process threads is all managed by the kernel. Because of this, kernel-level threads are slower than user-level threads. Advantages of kernel-level threads. Some of the advantages of kernel-level threads are multiple threads of the same process can be scheduled on different processors in kernel-level threads. The kernel routines can also be multi-threaded. If a kernel-level thread is blocked, another thread of the same process can be scheduled by the kernel. Disadvantages of kernel-level threads. Some of the disadvantages of kernel-level threads are a mode switch to kernel mode is required to transfer control from one thread to another in a process. Kernel-level threads are slower to create as well as to manage compared to user-level threads. Multi-threading models. There are three multi-threading models, namely many-to-one multi-threading model, one-to-one multi-threading model, many-to-many multi-threading model. Many-to-one multi-threading model. The many-to-one model maps many user-level threads to one kernel-level thread. This type of relationship facilitates an effective context switching environment, easily implemented even on the simple kernel with no thread support. The disadvantages of this model is that since there is only one kernel-level thread scheduled at a given time, this model cannot take advantages of the hardware acceleration offered by the multi-threaded process or multi-process systems. In this, all the thread management is done in the user space. If blocking comes, this model blocks the whole system. One-to-one model. The one-to-one model maps a single user-level thread through a single kernel-level thread. This type of relationship facilitates the running of multiple threads in parallel. However, this benefit comes with a drawback. The generation of every new user thread must include creating a corresponding kernel thread, causing an overhead, which can hinder the performance of the parent process. Windows series and Linux operating system try to tackle this problem by limiting the growth of the thread count. Many-to-many model. In this type of model, there are several user-level threads and several kernel-level threads. The number of kernel threads created depends upon a particular application. The developer can create as many threads at both levels, but may not be the same. The many-to-many model is a compromise between the other two models. In this model, if any thread makes a blocking system call, the kernel can schedule another thread for execution. Also, with the introduction of multiple threads, Complexity is not present as in the previous models. Though this model allows the creation of multiple kernel threads, true concurrency cannot be achieved by this model. This is because the kernel can schedule only one process at a time. That was a brief introduction to multi-threading models. Thank you.